Part 197 is all data, okay? So line 18H, transport, diffusion, phenomena, fluid mechanics, 5G Wow Seti. And this is a theory. Transport phenomena, quote from Wiki. Transport phenomena is in engineering and physics. The study of transport phenomena concerns the exchange of mass, energy, and momentum between observed and studied systems, while it draws from fields as diverse as quantum mechanics and thermodynamics. It places a heavy emphasis on the commonalities between the topics covered. Mass, momentum, and heat transport all share a very similar mathematical framework, and the parallels between them are exploited in the study of transport phenomena to draw deep mathematical connections that often provide very useful tools in the analysis of one field that are directly derived from the others. While it draws its theoretical foundation from the principle in a number of fields, most of the fundamental theory on the topic is a simple restatement of basic conservation laws. The fundamental analysis in all three subfields of heat, momentum, and mass transport are often grounded in the simple principle that the sum total of the quantity being studied must be conserved by the system and its environment. Then the different phenomena that leads to transport are each considered individually, with the knowledge that the sum of their contributions must equal 0. This analysis is useful for calculating any number of relevant quantities. For example, in fluid mechanics, a common use of transport analysis is to determine the velocity profile of a fluid flowing through a rigid volume. Transport phenomena are ubiquitous throughout the engineering disciplines. Some of the most common examples of transport analysis in engineering are seen in the fields of process, chemical, and mechanical engineering, but the subject is a fundamental component of the curriculum in all disciplines involved in any way fluid mechanics, heat transfer, and mass transfer. It is now considered to be part of the engineering discipline as much as thermodynamics, mechanics, and electromagnetism. Transport phenomena actually encompasses all agents of physical change in the universe. Moreover, it is considered to be a fundamental building block which developed the universe and which is responsible for the success of all life on Earth. However, the scope here limits the transport phenomena to its relationship to artificial engineered systems. So there's an overview. It talks about the physics transport are irreversible processes of statistical nature stemming from the random continuous motion of molecules. Mostly observed in fluids, every aspect of transport phenomena is grounded in two primary concepts: the constitutive and the conservation equations. The conservation laws, which in the context of transport phenomena are formulated as continuity equations, describe how the quantity being studied must be conserved within the universe of the question. The constitutive equations describe how the quantity in question responds to various stimuli via transport. Prominent examples include Fourier's law of heat conduction and Navier-Stokes equations. Those two have come up before in the Wow Seti signal, which describes, respectively, the response of heat flux to temperature gradients and the relationship between fluid flux and the forces applied to the fluid. These equations also demonstrate the deep connection between transport phenomena and thermodynamics, a connection that explains why transport phenomena are irreversible. The molecular transfer equations of Newton's law for fluid momentum, Fourier's law for heat, and Fick's law for mass are very similar. One can convert from one transfer coefficient to another in order to compare all three different transport phenomena. So there's the different equations that go with those, okay? So I'm assuming these are going to be part of the picture. J probably is for joules, and dt, velocity, okay. So Reynolds analogy, this has come up like 4 times. The Reynolds analogy assumes that the turbulent diffusers are all equal and the molecular diffusers are okay. So anyways, this Reynolds analogy has come up like in 4 different videos. So I'll have to take a look at that and see why. So we're going to go on to the next video.